In algebra, synthetic division is a method of performing polynomial long division, with less writing and fewer calculations. It is mostly taught for division by binomials of the form. But the method generalizes to division by any monic polynomial, and to any polynomial. The advantages of synthetic division are that it allows one to calculate without writing variables, it uses few calculations, and it takes significantly less space on paper than long division. Also, the subtractions in long division are converted to additions by switching the signs at the very beginning, preventing sign errors. Synthetic division for linear denominators is also called division through Roughness rule. Regular synthetic division, the first example is synthetic division with only a monic linear denominator. Write the coefficients of the polynomial that is to be divided at the top. Negate the coefficients of the divisor. Write in every coefficient of the divisor but the first one on the left. Note the change of sign from a 3 to 3. Drop the first coefficient after the bar to the last row. Multiply the drop number by the number before the bar, and place it in the next column. Perform an addition in the next column. Repeat the previous two steps and the following is obtained. Count the terms to the left of the bar. Since there is only one, the remainder has degree 0. Mark the separation with a vertical bar. The terms are written with increasing degree from right to left beginning with degree 0 for both the remainder and the result. The result of our division is evaluating polynomials by the remainder theorem. The above form of synthetic division is useful in the context of the polynomial remainder theorem for evaluating univariate polynomials. To summarize, the value of it is equal to the remainder of. The advantage of calculating the value this way is that it requires just over half as many multiplication steps as naive evaluation. An alternative evaluation strategy is Horner's method. Expanded synthetic division. This method generalizes to division by any monic polynomial with only a slight modification with changes in bold. Using the same steps as before, let's try to perform the following division. We concern ourselves only with the coefficients. Write the coefficients of the polynomial to be divided at the top. Negate the coefficients of the divisor. Write in every coefficient but the first one on the left in an upward right diagonal. Note the change of sign from 1 to a 1 and from a 3 to 3. Drop the first coefficient after the bar to the last row. Multiply the drop number by the diagonal before the bar, and place the resulting entries diagonally to the right from the dropped entry. Perform an addition in the next column. Repeat the previous two steps until you would go past the entries at the top with the next diagonal. Then simply add up any remaining columns. Count the terms to the left of the bar. Since there are 2, the remainder has degree 1. Mark the separation with a vertical bar. The terms are written with increasing degree from right to left beginning with degree 0 for both the remainder and the result. The result of our division is equals for non-monic divisors equals, with a little prodding, the expanded technique may be generalized even further to work for any polynomial, not just monics. The usual way of doing this would be to divide the divisor with its leading coefficient. Then using synthetic division with as the divisor, and then dividing the quotient by a to get the quotient of the original division. But this often produces unsightly fractions which get removed later, and is thus more prone to error. It is possible to do it without first dividing the coefficients of by a. As can be observed by first performing long division with such a non-monic divisor, the coefficients of are divided by the leading coefficient of after dropping, and before multiplying. Let's illustrate by performing the following division. A slightly modified table is used. Note the extra row at the bottom. This is used to write values found by dividing the dropped values by the leading coefficient of. Next, the first coefficient of is dropped as usual. And then the dropped value is divided by 3 and placed in the row below. Next, the new value is used to fill the top rows with multiples of 2 and 1, as in the expanded technique. The 5 is dropped next, with the obligatory adding of the 4 below it, and the answer is divided again. Then the 3 is used to fill the top rows. At this point, if, after getting the third sum, we were to try and use it to fill the top rows, we would fall off the right side, Thus the third sum is the first coefficient of the remainder, as in regular synthetic division. But the values of the remainder are not divided by the leading coefficient of the divisor. Now we can read off the coefficients of the answer. As in expanded synthetic division, the last two values are the coefficients of the remainder, and the remaining values are the coefficients of the quotient. And the result is equals compact expanded synthetic division equals. However, the diagonal format above becomes less space efficient when the degree of the divisor exceeds half of the degree of the dividend. It is easy to see that we have complete freedom to write each product in any row, as long as it is in the correct column. So the algorithm can be compactified by a greedy strategy, as illustrated in the division below. The following describes how to perform the algorithm. This algorithm includes steps for dividing non-monic divisors. Python implementation equals, the following snippet implements the extended synthetic division for non-monic polynomials. See also, Euclidean domain, greatest common divisor of two polynomials, graph paragraph BNER basis, Horner scheme, polynomial remainder theorem, Ruffney's rule. References, Liang Guo Fan. A generalization of synthetic division and a general theorem of division of polynomials. Mathematical Medley 30, 30 €37. Li Zol. Short division of polynomials. College Mathematics Journal 40, 44 €46 doi, 10.4169/193,113,409 × 469,721. External links, Goodman, Len. Stover, Christopher. And Weierstein, Eric W., Synthetic Division, MathWorld. Stover, Christopher, Ruffney's Rule, MathWorld.